2018, scientists study an ancient galaxy, the catchily named MACS 1149-JD1. There, they find some of the oldest stars ever detected.
This particular galaxy is exciting because it's forming stars just a very short time after the Big Bang.
Those stars could hold clues as to how the cosmic web that supports the universe first lit up. But as astronomers study starlight from when the universe was just 250 million years old, they get a shock. The stars are not just made up of hydrogen and helium produced in the Big Bang. They also contain what astronomers call metals.
Metals in astronomy is everything heavier than hydrogen and helium.
No matter where it is on the periodic table, if you're not hydrogen or helium, you are a metal, even though that makes no sense. If I were king of astronomy, metals is right out.
The Big Bang only made hydrogen and helium. Anything heavier than that was churned up in the cores of dying stars.
The bright stars of this ancient galaxy, dating back to just 250 million years after the Big Bang, contain chemicals that were created in even earlier stars.
Some of them seem to be nearly the age of the universe, extremely old, and yet they contain elements that guarantee they can't have been the first generation. As old as these stars are, there must have been something that came before.
The earlier first generation of stars remains cloaked in mystery. How did the first stars ignite? And did they kickstart the formation of the first galaxies?
It sounds like a classic creation myth. It's out of the darkness, out of nothing, structure arrived, and from that structure, the galaxies, the lights in the universe turned on.
We've never seen a first-generation star, but physicists have a theory of how they formed and what they were like. Let's step even further back in time, to around 100 million years after the Big Bang. The early cosmic web is dark. There are no stars to illuminate it. But the universe is ready for stellar ignition. Cooled down after millions of years of expansion, the gas clouds clinging to the dark matter scaffold begin to contract. As the hydrogen gas clumps together, larger clouds form super-dense, ultra-hot cores.
If you can bring hydrogen together and actually get it hot and dense enough, hydrogen will begin to fuse into helium. There'll be a nuclear fusion reaction going on.
Simulations suggest that some gas clouds are hundreds of times the mass of the sun. The stars they produce are unlike anything that exists today.
So the stars around us today really top out at masses between, let's say, 70 to 100 times the mass of our sun. There's nothing larger than that.
These first stars were up to 1,000 times more massive than the sun. So if you plopped it in our solar system, it would extend all the way past Jupiter. So think about that. That is incredibly big. That scale is mind-blowing.
So what happened to these stellar behemoths?
The lifetime of a star has a lot to do with its mass. The more massive a star is, the more gravity crushes the interior up to high temperatures, and it burns through its nuclear fuel even faster. So, incredibly, the more mass there is, the shorter a lifetime you get for a star.
The first generation of stars are sort of like the rappers and rock stars of the universe. They live fast, they die young.
First-generation stars didn't live long enough to form complex galaxies, but they did set the process in motion. The lives of the first stars may have been rock and roll, but their explosive deaths in supernovas pumped the universe full of heavy metal.
In the galaxy today, we see a supernova maybe every couple of years, close to us every couple of decades. This must have been a fireworks show. Giant supernovas going off all the time, all around you.
That act of destruction is actually an act of creation. What a star does in its core is it creates heavier elements from lighter elements.
That first generation of stars must have been absolutely incredible. Simply exploding so quickly and unloading all of this wonderful new chemistry into the galaxy.
200 million years after the Big Bang, the remains of the first stars flood the interstellar medium with heavier elements like carbon, oxygen, silicon, and iron. Crucial ingredients for the next wave of stars.
It's such a beautiful story because suddenly the whole process of star formation changed, and it literally became easier to make a star.
Heavy elements suck heat out of the surrounding gas. Cooler clouds crunch down much faster. The smaller, second-generation stars form rapidly and in much greater numbers. Somehow, this mess of stars transformed into a network of young galaxies. But it wasn't easy, because as these baby galaxies formed, a breed of matter-hungry monsters appeared in the young cosmic web. 13.6 billion years ago, the dark scaffold that supports all the regular matter in the universe emerges, ablaze with stars. But how did this stellar array evolve into a structure littered with organized galaxies? It seems they formed under constant threat of destruction. October 2020, astronomers discover a monster lurking among the cosmic web's earliest structures, dating to 900 million years after the Big Bang, a supermassive black hole. 6 galaxies surround this cosmic giant, caught in its grip, seemingly linked to the supermassive black hole by filaments of the developing cosmic web.
It's like the universe has given supermassive black holes an umbilical cord.
It's like an all-you-can-eat buffet right there.
Supermassive black holes are hungry beasts. They feast on any matter that gets too close to them.
Supermassive black holes are likely some of the most powerful objects in the universe. They can be anywhere between 100,000 to 10 billion times the mass of the sun.
Supermassive black holes have been a nemesis for generations of scientists, not because of their fearsome nature, but because nobody knows how they grew so large so early.
I wish I knew where supermassive black holes came from. If I knew, I would have a Nobel Prize hanging around my neck, and I would wear it every single day.
As someone who deeply loves supermassive black holes, whose career is based on studying supermassive black holes, it is very frustrating to not know where they come from.
Regular stellar black holes are the collapsed cores of dead stars, ranging from 3 to thousands of solar masses. But supermassive black holes, those are a different beast. 13 billion years ago, not enough stars had lived and died to build something as huge as a supermassive black hole. Now, the cosmic web offers scientists clues about the black hole conundrum. We now know supermassive black holes grow among the lattice of the young cosmic web, gorging on the hydrogen gas that travels along the filaments. At the same time, when the cosmic web is lighting up, supermassive black holes appear to be stealing star fuel from the young universe. You might think that would kill a growing galaxy. And yet, most mature galaxies have a supermassive black hole.
They really dominate the physics of what happens in the centers of galaxies, and even how galaxies can evolve.
We think these galactic monsters have been around from the start. How then did the web's young galaxies develop around supermassive black holes? The Milky Way's supermassive black hole is called Sagittarius A star. It's around 27 million miles wide and weighs in at just over 4 million solar masses.